Welcome back to the lecture series on GPU architectures and programming. So, if we remember, in the last lecture we have been discussing how CNN pipelines work and what are the underlying computations that need to be done for such systems, and based on that we will just try to now figure out what is the nature task graph model for CNNs, just like we have discussed the task graph models for or more specifically the computational graphs that can be created for generic neural networks. So, before going to that, we will just do a quick recap of our back discussions on back propagation. So, what really happens is that if you remember, we are just doing this up to, so that we are again in back to the notations that we have discussed earlier. So, while completing the forward pass over a neural network, we were denoting the error term as this y minus o, right, where y is the column vector of true levels and o is the column vector of the predicted levels, like we discussed earlier. And then during the backward pass, which started with the layer on with the weight matrix W prime, we are computing the following quantities. For example, we first computed delta 1, right, which was a product term that we figured out. Essentially, delta 1 was like this y minus o multiplied by the derivative of the activation function, right, which again is a column vector, and each of the values represent the derivative of the function in that given layer, right. And once the delta 1 was computed, that actually helped us to figure out what is del j del w prime, and we have already derived that for this the expression is this A transpose delta 1, where A is the input matrix for that layer. It has been found by taking the input and doing a product with W and all that, like we discussed earlier. So, if you remember, we have the availability of delta 1 with us. Now, using delta 1 we can also calculate delta 2, like we discussed earlier. So, delta 2 is nothing but delta 1 times W prime transpose multiplied by again the derivative of the activations, right. And using delta 2 we can compute the derivative of j with respect to W, and this is given by x transpose multiplied by delta 2, where x is the input matrix for that layer, right. So, these are the different terms that need to be derived while doing the back propagation. Again we will just recall, like, so the one of the derivatives of the loss function is A transpose delta 1, where delta 1 is the error multiplied by f prime of the f prime z, which is the gradient of the activation, and the other, that is del j del w, this is computable as x transpose delta 2, where x is the input matrix and delta 2 is as is given using delta 1 and the other expressions here, right. So, if we are just using these values in a similar fashion, if there are more layers, then what would really happen? So, let us recall the previous things, like, so in our first neural network example, we just considered that there is a layer with the weights W, and then there was this layer with weights W prime, and we derived delta 1 here, right. So, if we are just doing a pictorial description, then delta 1 was delta 1 was this value and f prime, and then we will just multiply this with the A transpose, right, and that essentially gave me this derivative, the del j del w prime, right. So, that is essentially the computation we require for the last layer for W prime, and then we had this previous layer corresponding to W, and for that we next computed this delta 2, right, and for delta 2 we actually used delta 1, and then we got del j del w, we utilize delta 1 and then we multiplied by the previous layers weights transpose, and of course, we have the f prime and others, right. So, essentially as we can see that there is a dependency of the previous layers loss derivative on the last layer, right. Now, if we just take this relation into a cascade, then what is going to happen? So, suppose there are more such layers, let us for example, add one layer del w 0, right. Then we will have if we just continue like this, first we have calculated delta 1, we used delta 1 to calculate delta 2, right. We just continue like this. One small problem we have, I believe this should be delta w, it is not going to be w prime. So, just a minute, yeah. So, when we are doing this, yeah, this is w prime. So, when we are doing the del j del w, it is using w prime, which is the last layer, and if we are going to continue the same, then just like I am computing delta 2 and I am using delta 2 as delta 1 multiplied by w prime transpose. So, essentially w prime is the weight matrix for the layer in which I have computed delta 1, right. So, if we just try and segregate, here I have w, here I have w prime, the next layer. In this layer I have computed delta 1, in this layer I am computing delta 2 and I am using delta 1 and then w prime, which is basically the weight of the next layer, right, and then I have this f prime, right. So, what we are really trying to say is that this is going to continue, right. So, now if we bring in a new layer here, let us call it w 0. So, then we will have delta 3 here, and delta 3 we will just see that the same thing is going to continue. So, we will now have delta 2 and we will have w here, and then we will have f prime again for z 0, where this represents the gradient of the activation function in the given layer. So, when I am computing delta 3, it is delta 2 w 0, then f prime z 0, where this represents the gradient of the activation function of this layer, whereas for the previous it was just z, where it was the gradient of the activation of function of that layer like that, right. Now, so the gradient of the layer delta j delta w 0, that I can again figure out using x 0 transpose delta 3, considering that x 0 is the input matrix for this layer, right. So, the point is very simple. For every layer I can keep on computing these delta values, and then I am going to do a matrix multiply with the weight matrix, and then also a further matrix multiply with the activation functions output, right. So, that is how things are going to progress, right. Now, if I consider a very general scenario where I have these L layers and each layer I has a weight matrix W I. So, in general, as we have already discussed, in CNNs I have these different kinds of layers. For example, I have the convolution layer. So, in convolution layer I have these two inputs, right. So, I have the image input and I have the mask to be convolved with the image, and I get the convolved output, right. In pooling I have a transformed image input and I am going to downsample it, right. So, the H's and W's are going to change to H primes and W primes, right, whereas the other things remain same, right. And then I have the fully connected layer. So, in the fully connected layer I am having the weights and I am having the input transformed image, and finally, it gets reduced to a linear array full of different class members, right. So, if we are now trying to look into how the CNN computation goes on, so this would be more like a task graph representation for that. Okay. So, let us see how things are going on here. So, let us say this is my starting layer A0. So, that goes as an input to the first kernel KF1, let us call it. So, here the blue ones are essentially convolution layers and they are providing the so essentially you can think that I have a convolution with activation and I am getting the input for the next layer, right. So, I get from A0 I get it transformed to A1, from A1 I am again. So, let us say the green ones the orange ones are trying to represent pooling layers again. So, then again I pull it down and downsample I get A2, again there is a convolution layer. Now, of course, for every convolution layer I not only need the image, but also the mask. So, I have a W1 here as an input, let us say I have a W3 here as an input and so on so forth, right. So, I have a convolution followed by pooling, again convolution followed by pooling, like that. So, here I can think that these dots represent that there are more such different layers here, right. At the end I am going to have the fully connected layers, right. So, in the fully connected layers, let us say the green ones represent the fully connected layers operations, right. So, at the end of the fully connected layer, I will get the overall output of the network, right. From here I can compute the loss and then I can use this loss error, that is to get I can get y, I can compute the error, that is y minus o, and then I am going to use y minus o to compute the each of the previous layers delta values, right. Because we have already discussed here like how I can in general compute the delta values of the some layer based on the delta value of the previous layer and also use that layer's weight matrix and the activations gradient and all that, right. So, with this here we are getting the error and I am using let us say this matrix KB1, this kernel is actually representing the computation of delta 1 making use of. So, if you remember what was my delta 1. So, delta 1 just requires y minus o and f prime, right. So, there is no requirement for any input of the weight matrices, right. So, I get delta 1 here, but then when I use delta 1 to get delta 2, if you remember the expression of delta 2 with respect something with respect to the previous one in general is that you need the weight matrices transpose, right. You need A's transpose, that is why this A will be transposed here, right. So, the dependency is from A to here. So, this kernel is going to make use of A, is going to make use of the W of that layer in order to compute delta 2. Now, let us again review why this is necessary. So, as you can see this delta 2 is nothing but delta 1 the weights and the value of f prime, right, and then you are multiplying it with the input matrix in the backward propagation. But what happens when you are just computing the first delta? The first delta is y minus o into f prime and then you are multiplying this with A transpose, which is the input matrix to get the original loss function, right. So, coming here when I have to go from this delta 1 to delta 2, what is really happening? So, I am using this delta 1 and I am using this WL, this weight matrix, and I am going to use this A to get delta 2. Then I am again using delta 2 to get the previous one delta 3 and like that this will make progress, right. And then I come back to the different pooling layers, right, where again I will be computing this in the backward pass and I keep on computing KB1, KB3, KB1, 2 like that to get the all the delta values here, right. So, we are trying to show a task graph view of these different kernels that are going to perform these data transformations for the convolution layer, for the pooling layer and for the fully connected layer like that, right. Now, also we need to see that computing the delta 2s are or the delta 3s or the delta L's in general, that is not all, right, because what is my overall requirement? My overall requirement is to compute in general the loss with respect to the different weightage, right. So, let us represent this del j del w I by this text d w I, right. So, in general I can say that this k f I, they compute, these are the kernels which compute the output image matrices A i's, right. Then let us say k b 1 I, this represents the kernels which are actually responsible for computing the deltas in the backward pass, right. And similarly, let us say k b 2 I, this is a different class of kernel which uses k b 1's outputs, that is the delta L minus i's, and also these A's to compute the overall loss, because if you remember the final loss is basically this image matrix transpose multiplied by the deltas, right. So, that is the final loss. So, that is why I need these additional kernels with dependencies which are coming from the A's, right. So, I will just review what we exactly did. So, if you see, the computation of every delta depends on the previously computed delta times. So, every delta's computation depends on the previously computed delta's value. Let us say I am taking delta 2 and delta 1 and the previous layers weight matrix, right, as you can see here. So, delta 2 is going to use this w here. I think this should be yeah, delta 2 is going to use the weight matrix and the activation functions gradient, right. So, both of those. So, that is why I have this dependency here, right, and we are just trying to show that this activation function is available and the gradients outputs are also available here. Now, when are the gradients outputs available? Well, they get available immediately after you compute the A's, right, because finally from the A's you are passing them through the activation functions only to get the actual matrices, right. So, here you are using these W's and A's and the previous deltas for this k b 1 kernels, k b 1 type kernels to get the next layer deltas, right. So, they form one class. Then you use this k b 2 class of kernels for and they get as input the deltas as well as the A matrices for different layers to give you the losses with respect to the weights in that layer, right, and that is how it will progress, right. So, overall if I see a task graph based view of the CNNs forward pass followed by the backward pass, I start with these values of W 1, W 2, W 3 like this for all the layers, and at the end of the backward pass I am successful in computing the derivatives of all these layers weights, and then of course, we will do the obvious thing, which is we will just update these W 1s with W 1 plus d W 1, similarly like that for the other W's, right, and then we will do again the forward backward traversal like that, right. So, this is just like a dependency oriented view of the CNN computation. So, if we now try to have a look like how these different kernels or these different data parallel kernels are going to work, what are their dependencies. So, as you can see, you have the convolution layer kernel which is doing the operation of computing the image transform followed by the activation function operation, right. Then you have the pooling layer kernels here, right. So, convolution then pooling like that. So, that sequence will continue and then you will have the kernels for the fully connected layer. So, this is entirely a forward pass. Then you have functions which compute the loss values. So, this is the kernels for doing the loss value computation, and then you have these two set of kernels, one set of kernels which are sitting in the cascade and they are just computing the delta values for each of these different layers, and we have the other set of kernels which use those delta values. So, these are the k b 2 class kernels. I mean, this is of course our own labeling scheme here. We are using them to compute the differentiated weights, right, or the gradients of the weights, right. So, that is what we get as output from these kernels, and these are the outputs that we are going to use. Now, of course, we will be using them to update the W values for the next forward pass. So, that is why their outputs go again to the second instance of the same kernels in the forward pass. So, as you can see that forward pass kernels kf1, kf2 all of them had a superscript 1. Now, we are just changing it to a superscript 2, right, just to highlight that this is the second iteration over the forward pass. So, I have the kf12, kf22 like that convolution followed by pooling again such sequences and followed by the kernels in the fully connected layer. Then again I go to the loss function kernel for a second time. So, it is the same kernel, right, is just operating on the second iteration, right, and this loop again leads us to the sequence of kernel pipelines for computing the delta values and also the DW values, which are this which I get just by using the deltas and the weight matrices, and then again this continues, right. So, all the outputs of this set of kernels in the second iteration will be again passed to the forward pass kernels for their third iteration, and that is just like an unrolled view the overall dependency graph, right. So, essentially I can say that in my system I have got this set of parallel kernels which are working, right. Here I have the forward pass, the loss computation, the backward pass, and it keeps on happening for multiple iterations inside a loop with the updates going on, right. So, this is like a task graph view for the convolution training part, right, through which we can, once it converges, we get the updated weight values. But then the important part that we want to discuss, like, well, we have the task graph view, but we have also understood that all the operations that are really going on, which is basically the delta computation, right, it is all general matrix multiplications, right. So, as you can see, the loss matrix multiplied by the gradients of the activation, and then again using each of the layers deltas with and multiplying them with the layers weights, right, to get the previous layers deltas, and again you continuing like that, and also in each layer using the value of the delta and the value of the corresponding image. In case it is an input layer, then it is the input image. If it is an intermediate layer, then the image transformed image available for that layer, so on and so forth. So, finally, all of them are general matrix multiplications, right. So, fundamentally that is where we have to optimize, right. So, that is why this generalized matrix multiplication is considered to be the core kernel in deep learning, and it is being used in both the fully connected as well as the convolution layers, right, because we have already seen earlier how that convolution operation is simply converted to the GEM by doing a simple image to column transformation. And for doing this, there exist several optimized implementations for GEM, and previously we have discussed some tiled shared memory implementation, and we will just focus a bit more on optimized versions of the same, right. But there is something interesting we would like to talk about here, which is like of course, this idea of multiplying large matrices has been there for quite a while, right. People have been working with such large matrices and multiplications, large matrix multiplications. And if you see, there are popular routines for scientific computation like BLAS, which implement underlying Fortran libraries which have been doing this matrix manipulation operations very efficiently, but one issue is these libraries assume a column measure format. So, that means the data is stored in the matrix, not in the when we are storing the data in the matrix, we are not assuming that the storage is row wise, but rather it is like this, right. So, it is a column measure format, and the issue is so in the memory when I am storing, I am traversing the matrix column in a column measure fashion, right. Now, when I am going to do a column measure traversal, of course, the access expressions for the matrix are going to change, and the important thing for us is this idea of column measure format of matrix storage has got carried forward into modern scientific workloads for where in popular libraries like the CL+, which is the OpenCL version of BLAS, and also CU BLAS, which is the CUDA version of BLAS, right. For example, if you just have a loop, here we are just providing a simple example of a 3-level for loop for matrix multiplication, assuming a column measure representation of the data. So, what is really going to change here? So, if you consider a column measure representation of the data, then when in terms of math you are trying to multiply matrix A and B of dimensions m cross k and k cross n, in reality you will have the matrices arranged in the other way around, right. So, that would be like k and m, and similarly here, right. So, there is a transformation, right, it is just like a transpose, but that is it. I mean, we have to live with it. That also means when you are trying to access data points, so whatever was some a I j in my original program, that is going to change to some a j I, right. So, that is sorry, if I just write it more clearly. So, it is different here, right. But the problem is that also means that your programs are going to now change, right. So, when you are really writing a row measure code, your matrix multiplication loop internally would have been multiplying like this, right. So, you may have been multiplying entities like A I k multiplied by B k j like that, right, where you are iterating over k. But now, that is really going to change. Well, mathematically if it is so, then in terms of the code, when you are trying to see what is the memory access expression, if this is the mathematical point that you are trying to use, that is you are going to multiply A I k and B k j, but here in terms of memory access they will be at different locations, right, because since you are accessing in a column manager way. So, you have to think it the other way around, and essentially you are going to use some something different. So, here let us say for example, in my code the iterators are m, n and k, right. So, let me just consider it here that it is all m's and n's, right. Like this, right. And then since we are taking it column measure, so really we should have to think of the a k mth entry, right. So, that means basically what is the mathematical location is a m k, but in our memory for where the storage is in column measure fashion, the element to access must be the other way around. That means, considering in a row measure way if it is a k small m. So, you multiply k by capital M, right, number of rows, and add small m, and similarly for the other one. The mathematical entity is b k n, but when you are accessing the real entity in memory, since the storage is in column measure format. So, we need to we just take it the other way around. So, we will have n multiplied by the iterator here, considering that we are multiplying matrices of this size m cross k. So, A is of this dimension and B is of dimension k cross capital N. That is why for the first one the entry I was looking for was A small m small k. you write it the other way around, that is you take the small k and multiply with m and add small m here, right, because it is column measure, and then for b small k small n, right, you take it the other way around, you take small n and multiply it with the capital K and add small k, right. So, that is a shift, right. So, this is a change that we have to keep in mind when we are doing the matrix multiplication operation, assuming that the data is stored in column measure format instead of row measure that we normally do for C and similar languages, right. So, this is the naive C code for C based C program like implementations of matrix multiplication. In the next lecture, we will touch upon the parallel versions assuming column measure data storage, and we will see how optimizations can be done for that. With this, we will end here. Thank you.